Hello everybody and welcome to CS. Ooh, that's scary looking. Okay, there we go. CS 202 online. Hope you all had a good weekend. So today we're going to talk about recursion. And really all you need to know about recursion is that recursion is recursion. And yeah, that is pretty much it. Now, if you would like to know more about it, then maybe we can try and look at it in more detail. So, first of all, let me give you a definition. First of all, are you guys here? Actually, I should probably check that to make sure. The stream, because I had some issues earlier. So, yes, it does say that we are live. Okay, cool. All right. The lesson is done. Recursion is recursion. I mean, frankly, I was going to just go ahead and be like, okay, see you guys. But I was like, no, it's too much. But yeah, okay. So essentially, let me go ahead and give you the book's sort of definition of recursion, and then let's kind of go from there. There we go. Come on. Okay. So recursion, and I did do a thing here that recursion is just recursion, which is recursion, which is recursion, which is recursion. So, yeah. Basically, it's the process of solving a problem. So it's one way of solving a problem. And the important part is how you do that, which is by reducing it. Makes sense so far. To smaller versions, which makes sense if you're saying the word reduce, of itself. So to take a quote from the movie The Matrix, recursion is not something that can be told. It's something that must be shown, right? So really, the best way for me to show you recursion is to just give you examples after example after example, and then you'll eventually catch on. There are some important concepts behind recursion that we will talk about, things like base case and recursive case primarily, but really, you just have to kind of see it first and get a feel for it, okay? So, as I said last week, we have finished with C++ technically. Like now we're not going to learn any new techniques on C++ or new syntax or things like that. For the rest of the semester, we are learning concepts, and we're also learning some data structures like linked lists and stacks and queues potentially. And so to be able to understand certain kinds of algorithms that are out there, it makes sense when you're trying to explain an algorithm to say that you're solving it by making it into smaller pieces. And so let me give you an example of something that is very, very nice to use recursion on. You don't have to, but you can, okay? And you still don't quite know what recursion is. Like I said, it's not that easy to kind of go over. And that is Fibonacci sequence, okay? So let's make sure we're on the same page on what the Fibonacci sequence is. So the Fibonacci sequence, and depending on what you ask, ooh, that sounds nasty there, but yes. And who you ask is going to start either at 0 or 1, but after that, it's going to be the following sequence of numbers. And these numbers are not random at all, especially once you know the pattern. The pattern is quite simple for them. To be able to compute the next number in the Fibonacci sequence, and maybe I should put little commas between them so that it's easier to see the separation of numbers. There we go. The way Fibonacci works is the next number in the series of this is computed by taking the last two numbers and adding them together. Okay? So, for example, if you want to compute the next number after 8, which of course we're looking at is 13, but if you want to compute it, what you do is you take 5 plus 8. 8 being the last number that you've seen so far, and 5 being the second to last number, right? So 5 plus 8 is 13. So from 13, how do you get 21? you basically add 8 plus 13, which gets you 21. So the next number here would be what? What would be the next number that we would see here? Void font string C out. Hello. I don't know why that you got censored for writing code. That's strange. Probably something in there is like cause bad words. Who knows? But anyways, yeah. So what will be the next number in the sequence here? It would be whatever 34 plus 55 is, which would be 5 plus 4 is 9, and 5 plus 3 is 8, right? 7, 6, 7, 8. Yeah. So it should be 89, unless I did my math wrong. Yep. And then from there, the next number would be whatever 55 plus 89 is, and so on. Okay, so I think you guys get this whole Fibonacci sequence stuff, all right? Now, there are some special cases with the Fibonacci sequence, and that is the beginning of it. Because in the beginning, you have nothing, but then you have something, right? So it turns out that the first two numbers of the Fibonacci sequence are 0 and 1. And then you can compute the next number, right? Because here's the thing. If I just gave you one number in Fibonacci and said like, okay, 0, compute Fibonacci sequence for this, then you would be like, well, okay, but for the second number, I need the previous one and the one before the previous one. Okay, the previous one is 0. What's the one before that? Well, there isn't anything because it's the beginning, right? So you wouldn't be able to compute the Fibonacci sequence. So typically, they will give you a 0 or 1. Sometimes they'll say, like, depending on who you ask, Fibonacci sequence starts at 1, and so you get 1 and 1, and then you start computing. But you need to get two numbers regardless of this, okay? If you made your own Fibonacci sequence that started at a certain number, you'd need to give the first two numbers of that. They could be whatever you want, but you have to give them, okay? So in recursion, we call that the base case, and that is basically some basic, as base sounds, basic information that you need to be able to compute the remaining of the steps, okay? So let us say that we wanted to implement Fibonacci sequence in code. Well, right now we can do what is known as the iterative approach, right? Which is basically just using loops. So if I told you write a function that prints out the whole Fibonacci sequence up to like a nth number, being the nth index, you know, for example, this would be the 0 or 1 depending on how you're counting. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this would be like the 11th index of this, or 12th number technically. And so if you were to write a function that could print out like maybe the first 20 numbers, or simply just a function that takes a parameter and that's the number of numbers that it prints out, that would be quite simple to do actually. You can just, you know, do something like void Fibonacci and maybe take a parameter which is the number of Fibonacci numbers that you want to print out. And then you could basically just start printing them out. Again, the first two numbers, you could do as an if statement in the loop, but you could just also do them before the loop even starts by saying something like cout 1 or 0, and then maybe like a 1 as well. 0, 1. So let's just say we print them all spaced out by 1, okay? Like that. So we printed the first two numbers. Although actually, okay, no, because that, this could actually work in theory, but we are going to, we're going to store them in a variable somewhere, because otherwise it's going to be nasty. So we'll call them like previous and previous 2. Okay, so the previous one is going to be 1, and then previous 2, so like second previous is going to be 0, okay? So now if we want to, and then of course, I guess we could add the cout statement again as well. So yeah, let's just throw in the cout statement since we want to print out the list as well as computing it. So we'll print those out as well, okay? It doesn't really matter where you put that cout as long as it's before the for loop, okay? So then you just go ahead and you write your for loop. So you can say like for int I is equal to 0, and then I is less than n, I plus. And now what you want to do is compute the next number, which we'll call next, I suppose. That's a good variable. And what we're going to do is just going to add the last two numbers, which are of course in previous and previous 2. Okay, so that's going to add them. And then after that, maybe we can cout that result as well, since we're also printing it. So we can say cout next. So actually we don't need the quotes. And then maybe add a space after that so it matches like nicely spaced out. And then pretty much now all we have to do left is compute the next numbers. But we will do that in the next iteration of the for loop. But for that, we need to update the previous number and the second previous, because now what was the previous number is now going to be the second previous number, and the number we just computed is going to be considered the previous number. So they're basically going to shift down. And so if you think about like swaps, in how you do swaps, it's kind of how this works. So the second previous number is going to take what was in previous now, because we're shifting it. So like if we were looking at this number and this number, what we're doing is we are shifting that this way. So we'll call this previous, and then this is second previous. Oh, actually other way around, sorry. Second previous is that one, right? And so what we're doing is we're saying, okay, whatever previous is not going to be second previous. And then whatever we just computed is now going to be previous, because the next time we loop around, we want it to be that way so we can compute the next number, which would be always that. Okay, so that is basically saying take previous and put it in second previous, and then take whatever was in previous and put whatever we just computed in next, like such. And that is pretty much it, because the next time this loops around is going to go ahead and compute the next number, add it to the cout, and so on. So if we were to very quickly code this, so let me go ahead and code it for you so we can see that it works. There we go. And then maybe pop out that so that we can see it better. Let me copy it and paste it smaller so that it's actually all visible. So let's see what we can do with this. Okay, so right there, and then there we go. You can see pretty much all of it right there. Okay, so let's just go ahead and code that very quickly. So void fib int n, and then we have int previous is equal to 1, int second previous is equal to 2, or sorry 0, and then the cout statement, so cout 0 1, like that, no end line. If you want to make sure it prints out, you can of course do flush if you really want, and then from there we have the for loop. Forgot 2 on second previous. Did I? Oh, I did. You're right. On the actual code that I'm coding. Thanks. Good catch. Good catch. Okay. And then for int I is equal to 0, I is less than n, I plus plus. And then here we have int next gets previous plus previous 2. And then cout that next variable. Add a space to that so it looks pretty. I forgot to add an end line in the outside of the for loop, which I'll do here, just so it looks nicer. And then update the previous, essentially, and then update the other previous. It's very important that you do this in the right order. If you put these two lines in the opposite direction, then you're gonna lose the previous number before you update previous 2. So you want to make sure these two are in the right spot, otherwise things get screwed up. And then there's the end line that I was talking about. Okay, so I think unless I made a mistake, then I pretty much copied it as it should be. So let's go ahead and disable the iPad like that. And hey, look at that. That's the stuff from the last class with the vector that we did. I think I left that because I might want to look at that in a little bit. I might. You know, I might add some recursive functions to that at some point. But for now, let us go ahead and do that. Okay. There we go. Okay, compiled. And oh, you know what I need actually? I need to call the function so that you can see it happen. So let's go ahead and say we get the first 10 numbers in there. Okay. And as you can see, we got exactly the same set of numbers that we had, sequence of numbers that we had in the tablet, which was those numbers, okay? So that shows that our logic is sound. You can see right there both. You can almost see all the numbers there. You can see that they pretty much match. Actually, everything is great except I forgot to add a space, you know, because it has 11 there. It looks like an 11. So I just can fix that by putting a space there. And then it'll look fixed. Otherwise, it might look misleading. So there we go. Now that looks more appropriate. And yeah, it works great. So if we try like a really big number here, well, not really big, but like let's say 50, we can find out what that number is, which, oh, it's a negative. I wonder why it's negative. Do you guys know? It's quite it was something kind of related to all the issues we were having last time, kind of. Overflow, that's right, indeed. So the number is so big, it's bigger than the 2.1 billion that signed integer can do. And because of that, it is indeed overflowing. In fact, we can see that the last number before we see the overflow happen is this one. So when it's adding 1.1 billion plus 1.8 billion, that's a total of 2.9 billion, which is bigger than the integer can handle. And so therefore it is overflowing. So we could fix that by using something bigger to handle this. So that would require probably switching these to longs. We of course could use unsigned integer, but that wouldn't really help us. That would help us just get one more number, and then that pretty much would be the end of that. So not quite the best solution. So instead, this is better. So this looks legit. This 2.9 billion. There's a lot of numbers here, so like I can't, you know, I have to look at the numbers and see if it's right, but it looks about right. So like, let's see, this is billion. So this is 20 billion. So makes sense. It's 4, 8, 8 plus 12 is 20. Yeah, so this is about right. Let's make a Fibonacci sequence out of big numbers. You know, that's a good question. That's actually would have been a cool thing to do, actually, now that I think about it. Because like that can handle those big numbers. So yeah, that would have been cool. I don't have an actual like solution right on me that I can just post. Plus, I don't know. I mean, what if like somebody's still actually, technically speaking, the assignment it hasn't been submitted, so showing the solution would be great. But yeah, what you try it out. I mean, your code should work like this because you've overloaded the operators. So in theory, all you gotta change for big nums here is make this a big num here like that. Maybe pass in the big nums if you don't want to create them here. Otherwise, you can create them there, and then give it a try, and then it should work. You know. So here's the output again, so you can compare it. But yeah, that'd actually be cool. So yeah. All right. So anyways, that is the iterative version of Fibonacci. It's quite nice, quite elegant solution, very simple, but it does require a little bit of sort of finessing from what would be like a pure mathematical solution of this, because we have to have sort of this. First of all, notice two things. We have to manually set the first two numbers per se and then print them. This, by the way, you have to do regardless, I suppose, of recursion, I suppose, because that'll be your base case. But aside from this, you know, the for loop kind of makes you go around and then update values and so on. So I mean, it's nice, but it's not 100% like. If I hadn't told you this and I put you on the spot, like you've never heard Fibonacci before the day of the test, and I tell you to code it on the test, you might have been got a little bit like nervous, and you know, a little bit of sweat would have come out, because I mean, it might be something that might be obvious now, but it could have been a little bit tricky if you've never seen it before. So with that in mind, let me show you what the math people would represent this as. If we're opening a math book and you said, okay, how is the Fibonacci sequence represented? Okay, in that case, it would be represented in a format like this. They will put an F, and then they will put a subscript n. And what this means is to calculate the nth number of the sequence. And because these are math people, they're not going to start counting from 0. They're probably going to start counting from 1. Okay? So that's kind of like an exclusive to CS kind of thing. So they're going to say f of n is equal to f of n minus 1 plus f of n minus 2, right? And then they would have the base cases, which they would do something like f of 1 is equal to 1, and then f of 0 is equal to 0, assuming, I guess, actually if they do it like that, then that would be counting from 0. Otherwise, they would probably say f of 1 and f of 2 is equal to 0, 1, or if they want to use the base cases of 1 and 1, they could, okay? So it's actually possible that the math people will be starting from 0. Doesn't matter. I actually kind of naturally went that way, I suppose. So technically speaking, I think this is the syntax that the math people would use even furthermore. They would say something like f of n is equal to, and then they would put the little curly bracket. They would put this thing like this, I think. If any math majors are here, you guys can correct me. And then, or if you just know any better, you can correct me. And then they would say 1 and 0 for n is equal to 1, n is equal to 0, n is greater than 1. I think that's the syntax that they would use. Like that would be the pure math book syntax. But I'm not 100% sure. Something around this, okay? I prefer the one above it. But the point is that this is how they would represent the Fibonacci sequence. They would say that the nth number is based on the last two numbers, with the exception of the first two numbers, which are always going to be 0 and 1. Or again, if you're not counting 0 as part of the sequence, then it would be just 1 and 1, okay? But we're using this version of Fibonacci that starts at 0. So when you look at what we coded, so when you look at this code, and you look at this code, there are some similarities, fair enough. We have the idea of the addition right here. So we got the next number is computed from the last two numbers. So that matches. The base cases, we don't quite have the n in there that checks that, I suppose. Actually, technically speaking, the way we coded this, we would need an if statement to make it 100% right. Because here's a bit of an issue. Suppose I just wanted to get, technically 1 is 2 of the Fibonacci sequence. This I think will work still. Ah, no, it doesn't work either. Perfect. So this one doesn't, oh really? That interesting that this version. Yeah. Okay, this is good. So we have to modify our for loop because I'm saying I guess we got to figure out what 1 means. Does that one, the 1 should be starting from 0 to the second number, or do we just want one number out of that? But let's say that we want the second number. We want the first index. So in that case, we need to change this to make sure it doesn't go into the loop in that scenario. So we probably want to increase this to be 2. So that'll fix that issue. Okay, there we go. So that fixed that issue. However, if we pass in 0, yes, you are correct indeed. We got it around the same time. If we pass in 0, then this happens, right? So how do we fix that? Well, we have to kind of put a special if statement that handles that situation. So we can say like, if whoa, that's kind of cool. But I don't know how I did that. I don't know the syntax to make this easier. If n is greater than 0, then go ahead and do that. Otherwise, go ahead and just do the 0, right? So that'll fix the special case when we only have one number that is supposed to be printed, like such. Okay, so now that will work, and then this will work, and then of course this will work, and maybe one more, like 5. Okay, so yeah, we have to kind of patch it to kind of get it going, you know, to make it like the pure. Oh, okay, that's not good. So we broke this version of that. So maybe this is supposed to just be a 1, but then that messes things up. If I is equal to 2, 2 is less than 2. Yeah, so I think this might just have to be a 1, not a 2. Let's see if that one works with that. Okay, so it was a 1, not a 2. So Okay, so then we got fib0 is a 0, fib1, 1, 2, and then this works as long as we consider fib0 to just be like the first number, the first index, like array start from 0 kind of thing. Otherwise, then we could make that a 2, and then that kind of takes the other meaning of that as a second number versus the second versus index 2, which is the third index technically. So, but anyways, now it's a little bit nastier because we had to do that patch, but even will prove my point more when we get to the recursion that it's, while yes, this code and this code, this logic and this code is very similar, they're not one-to-one. Like, it's easy to convert this into iterative code because of how simple, simple in terms of like other nasty math equations can be. However, wouldn't it be nice if we could translate this math directly into code without having to do this weird, hacking of like if n is less than 0 or greater than 0 or blah, blah, and then having to think of a loop and all that? And the answer is, of course, yes, it would be great. And so this is where sort of recursion is going to come into play. It turns out that a lot of the times when you see math equations like this, they're recursive by nature. And so it makes sense that we can actually do recursive code because it makes converting math into code a lot easier. But that again comes back to the same problem. What does recursion mean? So the idea of recursion is, again, must show you by code versus telling you, is if you have a function which we're going to call foo, and you want this function to print out an infinite amount of letters H, or actually something cooler, LOL. They're going to print out LOL infinitely, okay? If you wanted to do that, you have two options. The first option is you can just do an infinite loop. Maybe a space after it, so our LOLs are more elegant. And so again, if you just wanted this function to print this infinitely, then you can just say like while true cout LOL. And this, I guarantee you, is going to spam the terminal with LOL, right? So we can achieve that power by writing it. Of course, the 1 is the equivalent of true, which is why that works. But you could also write the word true in there. You could write something that always values a true, essentially. Okay. In fact, maybe I should write the word true, just so it looks more nice than just writing the number 1. Okay. It's just that in C you can't true. You have to import the boolean. So, anyways, if we go ahead and call this function foo, then you're gonna see some massive spamming. Food. Okay. And bam, of course, it's running forever. It's not gonna seg fault, it's just gonna run forever. It's gonna really lag the computer after a while. So I'm gonna stop it before something bad happens to the stream. But as you can see, the LOL has taken over the terminal, right? Okay, so that's quite an easy program. But there's another way that you can do this. And the other way that you can do this is you don't need the loop. You can just say cout, but that's only, of course, going to print it once. Okay, but what does function foo do? Well, it prints out LOL once. Okay, so what if I call the function foo inside of foo? So what if I write a function call here that says foo? What's going to happen then? Well, the foo function is going to call another instance of foo, which is going to print out LOL as well. And pretty much this will continue also forever, right? Because this is like saying, go to the grocery store to buy milk, okay? And so for you to go to the grocery store to buy milk, you need to start the car to drive there, okay? But to start the car, you have to start the car. But then you're like, okay, but how do I start the car? Do I need a key or something? No. To start the car, you just need to start the car. So you're sort of circularly requiring something, of yourself. And that's kind of what's happening here. Because when this code is running, it goes line by line, starts out with the top of the function, and it says, okay, what do I need to do? I need to do LOL. Okay, next I have a function foo. This function foo means that the program execution of this function call stops, and then it generates a brand new function called foo that has its own LOL, and then it has another function call. So let's kind of take an aside here and talk about what is known as the call stack. So I've talked in the past, when I talked about dynamic memory allocation, about how pointers are stored in memory, and in general how variables are stored in memory. Well, it turns out that you also have to store in memory function calls. And by that I'm not saying at compile time. What I'm saying is when your code is running, you have your main and it's running some code. There's some local variables and whatnot. Those local variables are kept somewhere in here. That we already talked about. So let's say we have an int A, int B. But suppose that you get to the function called for fib. Okay? fib5. When that function call happens, main execution stops, Fibonacci runs, it computes the number, prints out whatever it needs to do, comes back to main, and then main continues, right? We know that logic sequence is happening like that. But think about it. How does that actually happen? Like what does that entail for this to work? Well, what that requires is while Fibonacci is running, we need to back up the context from main, which is the local variables, and pretty much that's about it, right? Because if we were to just throw that away, when we finish fib and came back to main, and let's say again here we have like an int A, and then we want to like see out A, we want to make sure that A does not get changed. It's still intact, unless of course we intended to change it using Fibonacci, the function. So the way that works is when you are calling a function, the context of this is backed up in the call stack. And then you create a new instance of the function fib and its local variables, which in this case are previous two, previous one, and next, right? It also, at the top, has to pass in all the parameters that you call it. So in this case, we only have one parameter, which is the int n. And then you have your local variables, previous two, and then I suppose next as well, and I, because that's technically variable 2 in the for loop, right? So we have those 4 things, and I guess they're kept, one at a time like that, okay? So if you were to do pointer arithmetic, you probably see that they're all like next to each other. So if a function calls another function, forget about this self-calling. Let's say that we had a third function called bar that just couted like omega low, and then that's all it did, then that would be okay. So like if I had this function, instead of foo here, if I went ahead and called bar, and again bar was just couting omega, then what would happen is program execution in foo would stop, you would run bar, and then come back to fib, or foo, or whatever, whoever's calling it. That's the thing. It needs to remember where it came from, right? Imagine if when you called a function, and then you called another function, then when that function finished, it went back to like main every single time. It would like lose the way where it's at, and you wouldn't be able to call functions inside of other functions, right? So the call stack, the job of the call stack is to be able to keep track of where to go back. So if fib calls another function, that function is going to happen here. And when that function finishes, it erases itself from the call stack and comes back to the previous function. So when fib finishes, it erases itself from the call stack, and then we're back to main. So that is the way that it keeps track of who called you, what your local variables are, and whatnot. And that also enables you that if you were passing something by reference instead of by value, what you do is you basically keep a little pointer to the previous call, because that's probably where the references came from. So like if you let's say that that fib had a second parameter that was passed by by reference, that was like the A from main. Okay, in that case it basically keeps a pointer to that location up there in the call stack, so it's able to modify on top of it. Otherwise you wouldn't want it to mess with it. This is also how scoping works when you think about it. Scoping is going to check in the local scope first, but then to see who is on the next scope, all it has to do is go up the call stack, because that's going to give you the next scope until you basically get to main, which is going to be the top of the bottom of the stack per se. Even though it's the top here in the picture, it's called the bottom. We'll talk more about that when we talk about the stack data structure. Okay, so why am I telling you all of this? Because I want you to understand that whenever you call fib, what's going to happen is it's going to create a local variable for, actually, let's talk about foo, not fib. Whenever you call foo, there's no parameters, sure. There's no local variables, actually. Cout is not technically a local variable. So really, all that's going to happen is it's going to allocate some memory, very little, but some memory to do the cout. Okay? But then it has a function called to foo inside of it. What that's going to do is it's going to make another instance in the call stack with its own set of memory, and then of course create another foo. And this is going to keep going essentially forever. Here's the problem. Each of those, even though there's no local variables, is going to take a little bit of memory. Now, of course, if all of a sudden we had like a random variable here, it's going to take even more memory, because every time that I make a foo, it's going to allocate 4 bytes for that integer, right? But even if I don't have that, there's a little bit of memory that is associated with the foo call, because it needs to be added to the call stack so that it remembers. There's no parameters, there's no this pointer because it's not a member function from a class, but there's a little bit of memory allocated. So what's going to end up happening is this foo is going to keep calling itself, and is going to keep growing the call stack. Okay, remember back to the idea of how the memory is split into two things. It's split into the stack and the heap. If this keeps growing forever, eventually it's going to overlap into the heap. Even if the heap was really small, if this keeps going forever, eventually it's going to go there. I mean, the heap could be empty, and this thing is still going to keep growing forever until eventually it just eats the entire memory. What happens then is, of course, the term that we love, which is stack overflow. Right? And so that's one of the big problems with recursion, that when you call yourself and there's no way to stop it, once you call this function, it's just going to keep calling it and making new instances of it. Each instance is going to do something, but it's going to keep making more and more and more and more until it runs out of memory. So let us go ahead and do that. And of course, that doesn't mean recursion is like useless and we hate it. We'll fix that, but you know, baby steps, I suppose. So we're going to get rid of the loop. And then we're just going to call foo. Okay? So we get a bunch of lulls printed. Not that many of them, actually. I mean, actually, no, it's quite a lot. But at the end of the day, we actually get a segmentation fault. So you're like, oh, my program is crashing. Let's try to debug it. So put in -G as a compile flag, run GDB on it, run it, and then we see segmentation fault, and we're like, where did it crash? Let's go ahead and type in backtrace to see where that happened. And you're like, it happened at line 20. Line 20, where is that? The cout. Okay, who called foo? It seems like foo called foo from line 21. Okay, who called that foo? Well, it seems like another foo called it. and another foo, and another foo, and another foo. You see that? So there's a bunch of calls. If I type return to continue, I think I can just, can I just do R? Yeah, I can use R. You can see that like there's a lot of foo calls here in the call stack. That's what, by the way, what backtrace means. Backtrace prints out the call stack. So this is what the call stack looks like. So there's over 1,000 of these. I'm actually quite impressed that it did that this many. I was not expecting it to do this, probably because there's no local variables. Frankly, I don't know how far this is going to go, so I'm going to keep spamming while I read your questions. Doc stack overflowing for the purpose of learning. Yes, we must destroy the stack for the good of the people. All right, okay, I got 3,000. I'm tired of clicking. So, impressive. Most impressive. Let's actually, let's put a variable in there and see how that changes. Ooh. Oh, okay, I thought that was actually, actually, is there a way to see the height of the call stack? Oh, shoot. Oh, I've done it. Oh, I thought it crashed. Let's add at least one variable in there, because that's just going to totally make things grow even faster, because now there's 4 extra bytes for each of the functions that is made. Well, I guess we can see each low is a function call, so there's still so many of them that we actually don't see at the beginning. Okay, interesting. And then I don't know what the command is in GDB to see the size of the call stack, unfortunately. But okay, all right, there's that. So, anyways, so you might be asking yourself, I mean, on one side we've achieved what we wanted, which is another way of spamming LOL, but the while loop version runs forever without a problem, whereas the recursive version kind of dies after a while. So yes, it is an alternative, but not quite, because it would require infinite amount of memory to be able to truly match the power of the for loop that can run forever. And the for loop one, by the way, uses like very little memory. Like, it's just a for loop. Yeah, sure, you got to keep the integer, the I. Actually, no, you don't, because it's a while loop. So yeah, you basically don't need anything of memory there. So it's a very small footprint. So you might be already asking yourself, what is the point of recursion? Let me be the first to tell you that recursion is great and amazing for some things, but also completely useless and inefficient for most. It turns out that recursion is great for translating a lot of math and some complicated algorithms into code that would otherwise be horrifying to see in non-recursive versions. But in practice, recursive code is always more inefficient than iterative code. Iterative code is, again, loops. Recursive being this, which is a function calling itself, essentially. This is recursion right there. Much easier to just show you that than to tell you. So why ever use it? Because again, when you get a 302 and you're talking about some complicated algorithms, complicated being a subjective term, but still, quicksort, ABL trees in general, graphing algorithms, these algorithms are very mathematical in nature, and it's very easy to explain them in terms of itself. Like, you know, if I told you, like, I need you to like clean the floor, like mop the floor, okay? If you're trying to figure out how to achieve that task, on one hand, you could like get it like the world's biggest mop and just like swing once and clean the full floor. But that's a lot of work. Like, that's like probably a workout, if even possible. What you could also do is say, okay, I'm going to clean the floor, but I'm going to split it into small pieces because I can more easily handle that. So like maybe I'll clean one tile at a time, you know, assuming this is like a tile floor. Or if not, like one room at a time, right? That might actually be too much, cleaning one room at a time. That will still require like a big swing, you know? So like maybe a tile will be kind of like achievable in one swing. So the point being that it's very easy for us humans to kind of think about splitting a problem into smaller pieces that we can more easily solve. Recursion is achieving that. Recursion is achieving that because it's saying, solve this problem using the same technique you're doing now, but apply it on a smaller piece of it so that we can eventually build up to solving the entire thing. In this case, it's saying, to print that, to spam the terminal with LOL, what we're going to do is we're going to just print it one time. That's it, just one time. And then call ourselves again to keep doing it. So conceptually, it makes sense when you think about this. We are saying print LOL and then do this process again. What is the process? To print LOL and then do it again. However, what we're missing in this is a way to stop, which we definitely need, otherwise recursion will be completely useless. The way we stop is we need to keep track between each recursive call of something we've done, because like, I guess a good example for this would be like if you have amnesia, okay? So you have amnesia, like Memento, the movie Memento, the person, every time he goes to sleep, the main character, he forgets everything. So he needs to write down in little pieces of paper what he did. And like, in fact, he needs to remember this, he has amnesia in the first place. And, oh yeah, it's another movie, that's right, yeah. That's like an abusive movie though, because like, he takes advantage of her in that movie, I think, if I remember. I think, yeah, because he's trying to see what works out. But yeah, anyways, but yeah, essentially, that's right. So ultimately, what needs to happen is you need to remember what you've done so that you can remember when to stop. Because go back to the mopping the floor example. If you're mopping the floor and you forget which parts you've mopped already, you can be like, okay, I'm gonna mop room 1 first and then go to room 2. So you mop room 1, you leave, you start mopping room 2, and then you finish room 2. And then you're like, okay, I'm gonna mop the next room. But you forgot that you already mopped the first room, so you go back and mop it again. And then you forgot you mop room 2, and you're basically going back and forth between these 2 rooms for infinity. Or until you die. Or you run out of water, I suppose. So that's where our base case is going to come in. The base case is going to be the sign of when to stop. And for the base case to succeed, we need to pass a parameter between each recursive call, so that, which basically is a note that says what we've done in relation to how much we want to do so that we know when to stop. And it's kind of like a cycle, but see, that's the thing. Cycle is an iterative concept. We have to sort of distance ourselves, socially distance ourselves, I suppose, from iterative concepts and start thinking in a recursive mindset. See, recursion is more than this. It's a way of thinking. It's a mindset for solving problems. It's not superior, as I said, to iterative. In fact, I suppose, like I said, it's inferior in terms of implementation. But it's kind of like a way of life. You have to sort of step back and start thinking in that way. And it's not something you can just switch on and off immediately. It's going to take more than just 202 and even 302 to really get comfortable with recursion. But it actually turns out, and I like to say this, some research was done. Some students were taught recursive approaches to solving problems instead of iterative first, like they learn functional programming as their first language. They found it easier than people that are learning recursion after they learn iterative. But guess what? When those people learn iterative, they found the transition to be harder than people that from iterative to recursive, which is pretty interesting. Because again, it shows how once we learn one way, we don't really want to change. We just kind of want to stick to the way that works. So yeah. So anyways, that's a little bit too philosophical. Let's go back to actual coding. So how are we going to stop this? Well, okay, let's say that we want to print out LOL, not infinite amount of times, because we can't really do that with recursion because it's going to run out of memory. So if you want to print something truly for infinity, you do not want to use recursion. That is a no-go. That will fail epically, as we see here, pretty quickly actually, within seconds. Even if you have the world's biggest computer with the most amount of memory, it would still fail pretty quickly because you're basically contained by the number of processes that can be sort of, or not process, the number of function calls that can be done in a second. So yeah. Let's go ahead and put a parameter then. We'll call it an int n. And this int n is going to be the number of times to print. So if we printed this number of times, then we are going to be done. So what we're going to do is we are going to call foo, but every time we call it, we're going to increase it by 1. Because That means that we printed it 1 time or 2 times or 3 times and so on. And then we're going to add our base case, which is basically just a return statement. Now, if we do it like this without a check, this is not going to do anything. It's going to call foo, and foo's going to return immediately, right? So what we need to do is we need to wrap that return statement in an if statement. What is that if statement going to be? Well, if n, which is our count of how many times we print out LOL, is greater than, say, 10, then that means that we have completed this. Okay? That's pretty much all there's to it. So we want to pass in an initial value to this, so we're going to pass in 0. And then again, it should print out 10 times. Alternatively, what I could do is I could also switch this to say pass a number of times I want to print. Maybe we'll do that. But here, let's run this first. We'll switch to that because that actually would make more sense now that I think about it. So as we can see here, we get LOL 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times, and then we start printing out the Fibonacci stuff. Okay? So this worked out pretty well, but I don't like this whole like hard coding the 10. So let's do it the other way around. So let's say that the number of the call here is how many times we want it to print. So in that case, we start out with the total number of times we want to print, but every time we print it, we've technically gotten closer to our solution. So we're going to subtract 1 from n. And then we're going to say that if n is less than 0, then we're done. Or I suppose less than or equal to 0 will work. I'm not sure which of the two it will be. One of the two will give us the right value. One of them will give us too many. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So okay, so there we go. So that was the way to do it. So yeah, so let's kind of look at this code more carefully. So we got the function call. We have a parameter. This parameter is initially 10, okay? After it's 10, we pass it in here, and then from that 10, we check if n is less than or equal to 0. In this case, 10 is not less than or equal to 0, so the return statement does not run. So what does it run instead? You get the cout statement, and then you get the function call. But foo, which was, n is currently 10, so foo was called with 10, is not going to be called with 10 again, because that would make us loop forever. Or not loop, but recurse forever. It's instead going to be called by n minus 1, so 10 minus 1 is 9. So the next time we see this, we actually see a 9. So let me maybe pull up this here and kind of draw that out. So we're going to draw this out and say that foo10 is eventually going to make a call in the call stack to foo9, which is going to make a call to foo8. Let's keep going until we get to about foo2. And then from there, foo2 is going to say if n is less than or equal to 0, it's not. So we keep going. We see out another LOL. And then we get foo1. 1 is still not less than or equal to 0. Then we're going to get foo0. Okay, foo0, now n is indeed less than or equal to 0. It's actually equal. So 0 is equal to 0. In that case, we do not print out lol. We do not call foo. Instead, we see the return. So then, in our massive call stack, it's going to essentially clean this out, get rid of that, kick this out, because it's going to come back to foo1. Foo1 just finished from the foo call, which is line 23. The next line from that is the curly bracket, which means that the function is done. So then this gets out of the call stack. Same thing with foo2. Foo2 just finished in line 24, so it comes out. So basically it unwinds basically all the way back to the original foo10, which then is also going to finish. And then on top of that is going to be whoever called foo10, which was the main. So this will get kicked out, and then we're basically back to that context, and then it starts running the Fibonacci. So then it runs Fiv0 and so on. Okay? So this is more of proper recursion. So as you can see here, we have a way of stopping the recursion. And again, each function call does not have any connection with any other of the function calls. It's amnesiac. So the only way that you can communicate things so that you remember where you're at is with this parameter. So that's one very common approach when dealing with recursion is you want to pass parameters between the function calls so that you know where you're at, where you need to go, where to stop. You could also use, like, what other ways could you do this? There are less elegant ways. Like, I could keep a global variable. I could have made int n be actually a global variable, and it would not be part of this function, and this would still work the same way. Like, I could do this. Let's call that one like oof instead of foo, because we are using global variables, so it's like oof. And then we'll call this f, and that. And then we'll say if f is less than or equal to 0, return. And then we can say like f minus minus. Okay? Yes, I was going to get to that next. So you can also use statics for this. That's kind of like, I suppose that's like in between. It's not as bad as globals, but not as good as not using statics. It's kind of like an acceptable middle ground. But yes, you can definitely use it. So anyways, if I do oof now, I can say something like f gets 10 and then call to oof. Oh, make sure that you don't call to oof and not foo, otherwise bad things will happen. And I mean, well, I have to add an end line between the two functions. But you saw that it pretty much worked. Like such. See LOL and then LOL again. Fifth can be implemented as recursion passing in prepper to an n, right? Can be implemented a lot easier than that actually. So that was the last thing that I was going to do for the day, was make Fibonacci into recursive. But yes. So before I do that, I want to point out that yes, the global implementation will work. However, it's just like people will see that and walk away, just like no, be like nope, I'm not dealing with this code. So yes, as your colleague very well said, you can indeed use static variables, which is like not as bad as globals, but not as good as not using statics. Statics are kind of like the sellout sort of thing. I don't know, sellout's kind of mean sounding, but typically what that means is like in my 302 assignments, I tell them like, no, you can't use statics because like you guys know better than that kind of thing. So you might see like a resistance from people when using statics, but they're an acceptable solution. At the end of the day, I mean, you're coding to get a job done. You're not coding to make. I mean, well, actually, you might be coding to make like a work of art. You know, code is beautiful kind of thing. But sometimes you just want to get the thing to run and do the job like dirty. So there's an argument to be said for. If something can be done quicker but not as pretty, you know, if it works. So yeah. So anyways, how you do a static here would be like s is equal to 0. And then you could say something like if, pretty much the same thing. So let me just copy this actually. If trying to see how you want to, how can I do the static as a parameter? See, even trying to implement this with statics is strange. So let's say that I still want that flexibility. I can't use that. I think I have an idea. It'll only work one time though, but it'll work. So let's say that we got our int n, and we can say if s is if s is less than or equal to n. I'm trying to think if there's a way that I can't, without hard coding it, to only work for 10 with the static. Okay, let's just hard code it because I can't think of, I mean, this might work, but you're using a parameter anyways. So if you don't want, if you hard code that, like s is equal to 10, then you could do what we had before. But there's probably a better way of doing that I can't think of right now. Oh no, I opened LaTeX by accident. Too few arguments in bar. Oh, so I never did that. So let's call bar, and let's put an end line at the end of that so that they can see all three of them. So there you go. But that's not quite, that's kind of more confusing than anything, so don't feel bad about that one. We'll come back to examples where statics actually help us do the recursion, even though there's better ways of doing it, but they still is a way of helping it. We'll come back to examples like that. This is kind of a weird one to use that for. So anyways, before I show you the Fibonacci one, which again is the end goal, let's talk a little bit, now that we kind of understand this idea of base case, let's just put that down in paper so that we remember that for like tests and when you're implementing it. So when you're writing a recursive function, there's a couple of kind of like a checklist that you want to check off before you try to run the program and crash Sally, basically. So you want one of each of these. You want a base case, which is how the recursion stops. So like when the recursion stops. So you want to check that when the recursion stops. And then you want a recursive case. Which is basically calling yourself. And by calling yourself, I'm saying calling the same function, like the function calls itself, okay? This is also known as the recursive, I think, definition. But yeah, you want to have those two components to any recursive function. I mean, technically speaking, yes, you can just have a recursive case and then like run forever until you crash. But in practice, in like real world practice, you need to have a base case, because recursion that does not have a base case will essentially crash the program event. First of all, you'll never be able to stop it, and two, it'll crash, as we saw, pretty quickly. So there is technically one third thing that you need, and that is, you know, do something to get us closer to a solution. But that's kind of a given. What that's saying is going to be like print out LOL, count Fibonacci numbers, whatever you're doing, getting you closer, right? A small step for mankind, you know, a small step for, you know, cleaning one tile in the process of trying to clean the entire house, right? So that tiny step is you have to put it in. So where do you put that in here? Well, it doesn't really matter too much where you put it. You have the option of putting it pretty much anywhere, like here, here, or here. You know, before the base case, after the base case, but before the recursion, or after both the base case and the recursive case. So yes, indeed. So yeah, in fact, depending on where you put the step to get you closer, and this is something you'll learn later on in like 26 and compilers and all that, is if you have code of this format where you have, you know, the cout lol. If this is happening before the recursive call, this is known as tail recursion. Alternatively, if you have the recursive call and then the foo part, you still need to have the base case before in either of these. So like, you know, base case has to be here for the second example. Second case I was going to say, but that's too much work case. And for this one, it doesn't matter. It can be either here or it could actually be like this. that doesn't really matter too much. Though typically you will see the base case done before the actual step closer. But again, you can implement most solutions of most problems in either of those, okay? But either of those is known as tail recursion. And here, when you have the recursive call before you do the step, which is the lull cout, that is known as head recursion. And this will play a big role when you're doing like languages and grammars and talking about compilers and solving stuff that frankly I've forgotten at this point, you know, but it'll be great. It'll be fun. You'll have a lot of great time doing this stuff then. Okay. So that's in your future, but just so you know the terminology in case you see this when you're looking at like a implementation of code and they're like, this is a, you know, implement this as tail recursion. And then you're like, what is that? That just means that the last thing of the function is going to be the recursion call, the recursive call. Whereas head recursion, you'll typically see the recursive call before the cout. A very simple example where it would be useful to do head recursion would be if you're printing out a list. So maybe next time I'll create an array and then use recursion to print out the array in both directions, forward but also backwards. With head recursion, you can print it backwards, and it's pretty cool. So because what you're doing is you're basically going all the way to the end of the list, and as you're unwinding the recursion, you print from the end to the beginning. So it's pretty cool. But we only got 5 minutes, so what I want to show you now is how we can achieve what we started with, which was Fibonacci in recursive. Okay? Again, the whole point of recursion is supposed to be to make implementing certain algorithms easier. I've already shown you that recursion is pretty much inefficient, you know, when it comes to solving a problem. If you time code the same code, recursive code versus iterative code, the iterative code will always win, like always win, okay? If it doesn't win, it's because there's some behind the scenes stuff going on, like Python has like mnemonic code, and I think it's called mnemonic code, or what's it called? I have a link that I was going to show you guys. I'll post it on the description, but there's it basically like saves, it remembers what function calls return so that it doesn't have to call the same function multiple times. It's kind of like dynamic programming. If you don't know what that term is, don't worry about it. We'll talk about, not really, we won't talk about that. We'll talk about it in 202 if you take that with me, but not this class. So yeah, forget I said that actually. So anyways, going back to this. So the whole point of doing recursion again is to try to convert stuff easily from like math to coding. So let's do that. Let's go ahead and do that finally for Fibonacci, okay? So for Fibonacci, this is one way of writing it, or like I said, the other way you can write it is you can say, let me copy and paste that, is this one, right? Both of these are pretty much the same thing, very math-like, like that, okay? They mean the same thing, just different ways of writing it. Okay, so let us write our recursive function. So we're gonna say that it returns the n number that we're trying to call this on, okay? Because that's what we're trying to do, is we're trying to compute the number. All we're trying to do is compute the number. But I guess also we want to cout it, since we did that before as well. Cout the entire list. So we're gonna call this fib again, but this time it's gonna be valid returning because we also want to be able to return the number. We're gonna still pass in a parameter, which is the n number that we're trying to print, which matches the n here. And then we need to do the two parts of this, the base case and the recursive case. Again, the base case always has to happen before the recursive case. If you don't, it's going to keep going for infinity. First thing you do when you wake up and you got amnesia is you look at your notes to know like what happened, basically. If you don't, then you're lost for the rest of the day. So we'll watch Memento. That's a cool movie. I haven't seen it in a lot of years actually, but I remember it was cool. I should watch it again actually. So I'll have to see if it's like on Netflix or something. So what I'm going to do here is I'm going to go ahead and write my base case. Now, nobody said anything about there only being one base case. You can have more than one base case. In fact, you can have as many base cases as you want. It could be all base cases and whatnot. So In this case, we're going to have two base cases. For when n is equal to 1 and for n is equal to 0. Why is that? Because look at how we wrote this. We said f1 is equal to 1, f0 is equal to 0. So it makes sense. It matches line by line from the math to the code. So in both of these cases, we are just going to return 1 or return 0, depending, I suppose, on which one it is. If we also want to see out, because I guess that's part of it, we also want to be able to see out things, then we can add that to this as well. See out 1 and see out 0. Okay? Finally, we need to compute the numbers with the recursive case. Okay, how does the math look? The math says we have to use this formula. What do you think the recursive code is going to be? Literally the same thing. In fact, I'm going to copy and paste it like that. And instead of using the word f, my function is called fib. So I'll put the word fib in there instead of f. Maybe move the plus like that. And then really, instead of this, just put a return statement. Bam, I'm done. That's the recursive version of Fibonacci. As you can see, it's literally the same thing as we did in math. And that's the power of recursion, that it allows you to convert things from math to code very easily. Now, yes, we don't do the cout part. So if we did that, then we would instead of putting return there, then I would create a variable temporarily so that I can both cout it and then return it. Or I could actually just call this twice. I could do that too, but that would make it even more inefficient. But we'll play more with this because technically, if you notice something here, is that it will print it backwards because we're using tail recursion. But I have to think for a second. But yeah, this is basically how you would compute the Fibonacci recursively. You have the two base cases because you got two numbers, the first and second, and then you have your recursive case, which computes any other number. So very, very, very similar to that. In fact, 3 lines there in the math equation, 3 lines of actual code. That again is the power of recursion. So hopefully this gives you a very brief introduction. Of course, we're going to spend a lot more time. We're going to talk about recursive trees next time with the Fibonacci sequence. We're going to actually put this in code and computer and play with it. But I just really wanted to take the day to just sort of introduce you into the concept of recursion so you kind of get warmed up to it. Because while in 202, we're not going to go that in-depth in recursion, it's just something that people struggle with throughout the CS program. And so, you know, one way to avoid that is to just kind of get you started with that as early as possible. Because by 302, you're coding these algorithms that are recursive. And if you don't understand recursion yet, it becomes a lot harder to do it. When it's the whole point of recursion is to make coding easier. It's not faster. It's not better. It's just to make coding easier. So if it's not making your life easy when you're coding it, then something is wrong. So because you're defeating the purpose of it. So, you know, that's why. That's really the reason why I want to make sure you guys are comfortable with it. So that's it. That's the class for today. Thanks for watching, and we shall continue on Wednesday. Unless there's any questions or anything. No problem. Thank you all for talking and being here and correcting some of the stuff with the code. See? That was efficient. We might be still debugging things right now. So, awesome. All right. Well, have a great week. I'll see you guys on Wednesday. See ya. Thanks.